much, Bill, Jeff, Philippa, for this wonderful introduction. So it's an enormous honor and privilege to receive this Lovelace Award from the British Computer Society. And it's also a great pleasure to have the occasion held here at Imperial College, where I spent many happy years, and in fact gave my inaugural lecture here just over 20 years ago, actually in this very lecture room. So there's a very strong sense of coming full circle. There's a few things I want to say about this before I start the lecture proper by way of acknowledgement. The first thing I'd like to say is that an award of this nature recognizes also the research community, which makes this kind of work possible. Science is a conversation, and if one's speaking to oneself and nobody's listening, it's not very fruitful and productive. And it's been a great feature of my career that there's been a very nurturing research community in which to work, which was willing to consider new ideas and directions, and with many people that I was able to interact with very fruitfully. I'd also like to say something in this connection in relation to BCS itself. In fact, this is when I was asked for some material for the press announcement when the award was made, I particularly wanted to make this point. I found it particularly pleasing that the award recognizes work of a highly foundational character, and therefore shows the commitment of BCS to support the study of computing, not only for its applications, but as a fundamental scientific discipline in its own right. And that's very much the spirit of the lecture that I'd like to give tonight. I'd also like to mention the various institutions which have provided a home for me, put up with me for various periods of time over the years, where I've spent happy times and had many wonderful colleagues. Queen Mary, where I spent 5 years, firstly as a research student and then as a lecturer. Imperial College, as Jeff was saying, I spent 12 very happy and formative years here in the Theory and Formal Methods group. The University of Edinburgh, Laboratory for the Foundations of Computer Science, and since 2000, the University of Oxford. And we now have a flourishing quantum group. And really, we could get into one of those Hollywood-type thank you speeches, so I can't mention all the people I've learnt from, often from their criticisms, over the years and interacted with and so on, but I'm enormously grateful for all of that. And I will mention some of the people I've worked with directly on the work I'll be talking about tonight. And just to mention a little sort of personal timeline, the most important point on this timeline is the first one. I graduated from university and gone to be my first job as a programmer, working on operating system development at GC Computers, as it then was. I fairly happily engaged in that. But it happened that an early report by George Milne and Robin Milner came my way. One of the other people there was a graduate and received from there and received the reports. And reading that was an early version of what later became CCS. Had a really big effect on me to really make me aware that computer science can be a fundamental scientific discipline, not just a collection of techniques. And this, I think, played a formative role in deciding a little later to leave that job and come back to university to do a PhD in computer science. Then some of the other things that have been mentioned and which are mentioned in the citation for the Lovelace Award, the work on domains in logical form, more broadly relating to connections between the semantics of computation and duality theory, the work on game semantics, which was the topic of my inaugural lecture given here just over 20 years ago, and work on categorical quantum mechanics. And I'm happy to say that all of these seem to be flourishing activities still. we recently had a meeting in celebration of Prakash Panagarden in Oxford a few days ago, and a lot of the talks there were about duality. It's a very active topic, and nowadays a lot of the focus is on duality in relation to probabilistic computation, and that's still a very thriving area in computer science. Game semantics has become a standard part of the toolkit not only in semantics of programming languages, but also in compositional and higher order verification and model checking. Categorical quantum mechanics is about to celebrate its 10th birthday this year. There's plans for a party, and there are a couple of textbooks based on successful courses which are being published this year. And what I'd like to talk about today, though, looking forward, is one of the main primary focus of my current work on contextual semantics. I couldn't resist showing some of the pictures from the earlier work, though. Some of you may have been sat here in this very room something like 20 years ago and may even remember these pictures here illustrating the ideas of game semantics. It's actually dangerous for me to look at these pictures because I have a strong temptation to talk about them. But I have another story to tell today. I would say, though, that I still think that these two pictures, properly understood, contain the essence of what game semantics is about. There are a lot of technicalities beyond that, but this is really the essential ideas. And to some extent, the same is true of another picture that many of you may have seen in various talks by myself or Bob Cooker or someone else, the information flow in quantum teleportation expressed in this diagrammatic formalism of categorical quantum mechanics. I managed to dig up this picture. I'm afraid it's a bit grainy, from the Theory and Formal Methods group from just about the same time as that inaugural lecture. A wonderful group which I took enormous pleasure in being a part of. If you're very keen-sighted, you can make out some of the people here. Actually, John Reynolds, you may recognize there, who sadly passed away last year, a former winner of the Lovelace Medal and a great computer scientist. He was on sabbatical visiting me in the group in that year. Chris Hankin is there. Abbas is there. Some of you may recognize Duško Pavlović wearing a very traditional cloth cap. Wow. And Guy McCusker in dreadlocks. Oh, and I'm afraid the chap filling the voluminous white shirt in the front row is me. So, let me turn then to what I want to talk about tonight. And I want to begin with the first axiom I learnt in computer science. Now, in general, we might not think of computer science as reveling in general axioms, but I did quite explicitly hear this. I mean, there are some. I mean, there's a famous one, I think, often attributed to Roger Needham, that all problems in computing can be solved by adding an extra level of indirection. The one that I learned, something like 2 weeks into starting as a PhD student, is this: computers might as well be made of green cheese. And that was exactly the way that I heard it expressed. So this seems rather curious. But what it means is, or the point of this, I'm not going to say who said it, by the way. What is meant is that the device physics is immaterial. Once the logical model of computation has been realized by whatever means, then computer science kicks in, and we don't need to worry about the physics. And for many purposes, and to a great extent, this is actually a very fruitful attitude to adopt. We can abstract away from the underlying realities of the hardware. However, as we've come to understand, it's no longer true in general to assume this. It really does make a difference what computers are made of, what their physical embodiment is. And this leads on to the idea of quantum computer science, the interaction between computer science and physics, quantum physics, that's happening because of developments in quantum information and computation. Of course, any information processing system is really physically embodied. Otherwise, it's not going to exist and it's not going to do anything for us. And the underlying physics of that is ultimately quantum mechanical. In fact, Feynman famously said that Turing's analysis of computation, you remember the sort of account of his wonderful account of the Turing machine as the activities of a human computer, human agent, performing the computation, writing in squares of paper. So everything is fine, except that that sort of assumes that we understand the pencil and paper. We understand and assume that the physical process is governed by the laws of classical physics. But ultimately, the physical systems in which computation is embodied satisfy the laws of quantum mechanics. And that can make a difference. And as we've come to understand, it does make a difference. So it's led to various exciting developments to the point where governments are now taking seriously the possibility that we're going to have to radically revise our existing crypto systems in the light of the challenges posed by the new algorithms, efficient prime factoring, and so forth. But beyond this focus on algorithms and complexity, I think it offers new challenges and opportunities across the range of computer science, also in the areas of programming languages, logic, and semantics. And as I see it, there's a fascinating two-way interplay developing between computer science and physics, both at the level of the foundations of both, raising new challenges and problems and creating new insights, as well as to, of course, more practical matters. And I was slightly proud of myself when putting this lecture together to realize I'd written this sentence in 2008. I mean, not that it was very difficult to see this coming, but in fact, the current quantum technologies program being funded by EPSRC is exactly in this spirit. And indeed, a lot of it is to do with information. So this is an exciting emerging area, attracting students with a wide range of backgrounds. We certainly see that in the quantum group at Oxford. And from my point of view, having taken on board the idea that computer science is a fundamental scientific discipline, computer science, as well as being a science, shouldn't just be a science in and unto itself, but actually it has very strong connections with other sciences, including the natural and physical sciences, many others as well, in fact. And these interactions between computer science and the other sciences, in my view, is where some of the most interesting current developments are happening. So that was a challenge and an opportunity that I felt I couldn't resist. And as Bill has pointed out, I tend to dive in when that happens. So what I particularly want to focus on in this talk are some central phenomena at the heart of what makes quantum different from classical. In particular, the phenomena of non-locality, contextuality, and entanglement. Things that are very hard to understand because they contradict our everyday intuitions and things that it seems we could take for granted. And yet, they play a central role in this rapidly developing field of quantum information. Not just in terms of being puzzling and creating challenges for the understanding, but in terms of creating new opportunities, new resources, informatic resources, which let us transcend the bounds of classical information processing. And at the same time, they have profound consequences for our understanding of the very nature of physical reality, because that's what we're talking about. What I'm going to do is describe recent work in which tools coming from computer science are used to shed some new light on these phenomena. And by trying to find the structures that are present in these phenomena, what we find is that we can extract structures which really arise in a whole range of areas in classical computer science, which on the face of it have nothing to do with quantum mechanics at all. So something as workaday and central in ordinary computing as relational databases tends to have a remarkable isomorphism with these apparently very esoteric phenomena in the foundations of quantum mechanics that we'll be looking at. So let's jump in and go to the heart of this quantum mystery. Now, at this point, you might be thinking, well, we're going to need to know a lot of physics, aren't we, to deal with this? Surprisingly, we can actually formulate the essential ideas in a way that I would hope would be meaningful to any computer scientist without any detailed knowledge of physical systems. In fact, I'm going to take this as my basic scenario. So we have Alice and Bob. We have to have Alice and Bob. They're our agents, sort of situated, if you like, at somewhere, maybe at different places in some network. Alice has two local bit registers. We call them A1 and A2. And what Alice can do on a step of computation is to load one of those local bit registers and test its value, either 0 or 1, right? And Bob can do similarly. And we can imagine that we can then collect their joint findings, their joint outcomes of these operations in some target. And that's one step, and we imagine this happening repeatedly. We imagine multiple rounds where this happens, and on different rounds, we may get different results. Even if Alice looks at the same registers, Bob looks at the same registers, on different rounds, we may see different things happening. And by doing this repeatedly, we can build up statistics for these experiments and extract probabilities from them. So here is a probabilistic model of an experiment like this. So what is this model, what is this table looking at? By the way, if probabilities make you nervous, don't worry, because we'll soon manage to abstract away even from the probabilities. But just to get a feel, because it's a bit more concrete, I think. So what is a table like this saying? Here are the various choices that Alice and Bob can make of which local register to load. And then we see that gives us the rows of this table. And the columns then correspond to the different values they could possibly observe when they load the chosen register and inspect it. And what we see in entries in the table, for example, this entry here, the highlighted one, says, if Alice looks at A1 and Bob looks at B2, then 1/8 of the time, what Alice will, in other words, 1/8 of all the runs that we perform, Alice sees a 0 and Bob sees a 1. And in general, you see if you go along each row, you have a probability distribution on the possible joint outcomes. So the question, so this is real behavior that we can all understand. And here's a particular table of numbers of probabilities reporting on our experimental findings for this behavior. And the question that it's natural to ask is, what kind of explanation can we give for this behavior? So here is, I think, if one thinks about it, the natural and essentially the only kind of reasonable classical explanation of how this could arise. What we imagine is something I call a classical source, which on each round is generating values for these local bit registers. So it writes values into all of the registers, and then whichever one it writes into a given register, if Alice chooses to look at that register, then that's the value that Alice will see, and similarly for Bob. And to account for the fact that, and so the fact that this happens on each round, that we're sort of generating this stream of values, will account for the fact that we don't necessarily see the same values for the same registers on each round. And what we can ask is, and we can imagine, since we're dealing with sort of statistical behavior, we can imagine that the source itself is probabilistic in nature. It chooses which values to write into these registers, maybe by tossing some coins or sampling some probability distribution. So that seems like a pretty general mechanism, and if we're going to have any chance of explaining what's happening in any ordinary classical sense, something like this should surely have to do the job. And the question is, can we use a classical source to explain the behavior that we see here? Now, we could, in fact, directly look at a table of probabilities like this, and there's a beautiful and elegant and quite simple argument that will answer that question. But I'm going to do something even simpler. As I said, we're going to ditch the probabilities. And I'm going to even throw away most of the information in such a table and just look at some even more basic information, if you like, of a logical character. In other words, we only distinguish whether something can happen at all, in other words, with some positive probability, or can never happen, in other words, with zero probability. So is it possible or impossible, which we can simply record with a binary distinction, with either true or false, 1 or 0. So for example, the entry in the top left is saying, if Alice looks at A1, or in those cases where Alice looks at A1 and Bob looks at B1, then it is possible sometimes, with positive probability if you like, Alice sees a 0 and Bob sees a 0. That's what this 1 in the top left corner is saying. Whereas the entry in the second row in column 1, this 0 is saying if Alice looks at A1 and Bob now looks at B2, then it can never happen that Alice sees a 0 and Bob sees a 0. Okay? So is it clear? That's what this possibilistic table is saying. And notice that not only have I thrown away all the information, the quantitative information about the probabilities, I'm actually not even considering all the entries in the table. It's enough to look at these 4 entries. And in the light, so we can fill in the others however you like. And in the light of this, we can now ask our question again, can we explain this behavior using a classical source? So can we, is there some classical source choosing values for all the variables, writing the values in, which will account for this behavior? So before answering that question, let's sort of step back a moment and say, you know, what's going on here if we now think about observing variables? If we think that what's happening is there's an objective reality, everything really gets a value, if we look at our picture of the system, then after all, at any given time, each of these bit registers is either 0 or 1. That's what we would usually understand. It has a well-defined state. So these are objective properties, whether we happen to look at the register or not. That's the sort of realistic or objective position that we would usually take from the point of view of classical physics. So if we try and make this a little more precise, what it's saying is that there's, in each possible state of the system, there's a function, let's call it lambda, which for each measurement, I'm now starting to use the language of measurements, which for each choice of a register by Alice or Bob, specifies an outcome independent of which other measurements might be being performed. So it has a well-defined value for whichever register Bob chooses to look at independently of whatever anyone else chooses to do. And that seems just common sense. But actually, this point of view is called non-contextuality. It's essentially equivalent to what the assumption of what we were calling a classical source. So we want to retrieve a common sense explanation of this kind of behavior, then this is how it cashes out. And the fact, what we can regard as the shocking fact, is that this view is impossible to sustain in the light of our actual observations of microphysical reality. So reality is not like this. How can that be? How should we understand it? These are why understanding quantum mechanics is a continuing challenge, but also why using it is a continuing opportunity. So if we take essentially the same picture we looked at before, but just interpret it slightly differently, we recover what is traditionally known in the quantum mechanical literature, the foundations of quantum mechanics literature, as the hidden variable picture. And here is in particular a sort of visual way of seeing one of the very nice accounts of this given by the physicist David Mermin quite a long time ago. And interestingly, Mermin chose the name instruction set, very much a computer science term, to give his explanation of hidden variables. So it's essentially exactly what we were saying before, that we now think of this as the unseen state of the system, the hidden variable, but it's exactly what we were describing as the classical source. The only slight difference is that we now think of these, instead of putting it in terms of these local bit registers and loading them, we now think of Alice and Bob as performing measurements. So they can choose which measurement to perform in exactly the way that Alice and Bob could choose which of the local registers to look at. but it has exactly the same structure. Now let's come back to the question we asked earlier. This table, this possibilistic table, can we explain it in terms of a classical source? So let's see. Well, suppose we could. Then everything that could possibly happen has to arise by virtue of one of these instruction sets, which might happen. So there has to be some lambda which could happen, which would account for the possibility of this entry in the top left corner. And clearly that lambda, just by the fact that it makes this possible, must be assigning the outcome 0, or the value 0 to A1, and the outcome 0 to the variable B1. Okay. But now let's see what else we can infer about such a lambda. Remember, this lambda, this objective description of the values everything has to assign values to all the variables, independently of which we happen to choose to look at. So let's look at what it can assign to B2. Well, it can only assign two things, either 0 or 1. Those are the only well-defined outcomes here. And this 0 here in the table tells us that it's not possible that we get this joint outcome 0, 0 for A1 and B2. Therefore, it cannot, in fact, assign 0 to B2. And the only remaining possibility is that it assigns 1 to B2. And we can now apply exactly the same reasoning, having fixed that it must assign 1 to B2 to the variable A2. We already know that B2 gets 1. If A2 got 1, then this event here would be possible, and this 0 in the table is telling us that it isn't. So the only remaining possibility is that it assigns 0 to A2. And now what we find is that there's a unique instruction set which can account for this possible event up here in the top left and be compatible with the constraints we have, some of the constraints that we have elsewhere in the table, and it's this. So that's a completely defined instruction set that assigns outcomes to all the variables. But now, of course, the trap springs because we still have this other 0 entry, and according to this lambda is saying that the outcome 0, 0 for measurements or variables A2 and B1 is possible. A2 gets 0, B1 gets 0, and this 0 in the table is saying that that possibility cannot happen. So in fact, what we're saying is that there is no lambda which is consistent with all the constraints in the table and which makes this event possible. And from that, we can draw a big conclusion. Hardy models are in fact contextual. They cannot be explained by a classical source. Whatever probability distribution we dream up, whatever way we have of choosing these instruction sets, they can never account for this observable behavior. So the conclusion we might then draw is that that just can't happen. We have no way of rigging up our system with Alice and Bob and setting things up in such a way that they will see that kind of behavior. But that turns out to be false. We really can achieve this kind of behavior, this degree of correlated behavior, if you like, if we use quantum rather than classical resources. So this is where the separation between the quantum and classical is made precise. If we use quantum rather than classical resources, this behavior is realizable. More specifically, if we use an entangled qubit as a shared resource between Alice and Bob, even though they may be far, far apart, then behavior of exactly the kind we have considered can be achieved. And in this way of thinking, we now, as we've already said, rather than thinking of these local bit registers, we should think of Alice and Bob as choosing measurement settings. So we can think of spin measurements, and they're choosing which direction to measure spin rather than which register to load. But it's really, the formal structure is exactly the same. So I'm not going to inflict a lot of quantum mechanics on you, but just to have a little brief look to get some sense of the sort of structures that come into play here. So we're talking about spin measurements, the qubit, the quantum replacement for the bit, in fact, for the bit register. And in this world, states of the systems could be described by complex unit vectors in two-dimensional complex vectors. And there's a beautiful way of visualizing these in the sphere. It should really be a three-dimensional sphere, but to keep the picture simple, I'll just draw these circles. The point is we can have a state of a system being anywhere on this sphere, on the surface of this sphere. I'm just going to talk about pure states. So we have a continuum of possibilities for the state of the system. And on the other hand, we also have a continuum of different questions we can ask of the system by choosing different directions to measure spin in. And these are represented by pairs of opposite points on the sphere, spin up or spin down in a given direction in space. Why should we think of this as some kind of a bit? Everything seems continuous. Well, the point is that there are only, if we choose the direction, whatever the state, and whatever the direction, once we fix the direction, there are only two possible outcomes, either spin up or spin down in the given direction. And that's where we see the appearance of quantization. So we get discrete outcomes from these measurements applied to these kind of states. And this is real stuff. I mean, the famous original experiment that identified this phenomenon goes back to the 1920s. So we have a stream of atoms, they're passing through this magnetic field. So we could think classically they're little spinning tops and they get deflected. But on that classical picture, we'd see a continuous smear of contacts on this plate here. And what we actually see, what nature actually shows us, are these discrete outcomes, spin up or spin down in the given direction. Okay, so that's the single qubit, already very different from the classical bit. It's not yet clear what it can do for us. Actually, we don't really reach non-classical behavior till we go to multiple qubits, and it's there where the phenomena of quantum entanglement arise. So here is a classic entangled state. So we think of it as two qubits, one held by Alice and one held by Bob. And it's possible to arrange this, maybe generating from a common source, so that Alice and Bob are far, far apart, in the jargon space-like separated, but nevertheless, there are these different parts of the system shared between them. And that's why various quantum communication protocols, such as are used in quantum key distribution and so on, come into play. Now, the key thing is that these states can be highly correlated. You see, we have, in this case, either the possibility of both being in the spin up in a given direction or spin down in a given direction. Mathematically, it's because we use a tensor product, a superposition of these different combinations of states. What that's saying is you cannot reduce the state of a compound system just to a product state, a state which is just put together from a state of system A and a state of system B. There can be interaction between them, which can encode high degrees of correlation. And this is what Einstein famously called spooky action at a distance. Even if the particles are spatially separated, measuring one has an effect on the state of the other. So for example, in this state here, if Alice measures in this basis and gets spin up, well, she might get spin up or spin down, but if she gets spin up, then if Bob were then to measure, even though he's far, far away, once Alice has got spin up, he can only get spin up, and similarly if Alice gets spin down. How can that happen? How can the world be like that? Well, we don't really know, but we know that it is like that. And we're beginning to find out how to make use of that. So Bell's theorem is that this kind of non-locality, this action at a distance, is an inherent property of quantum mechanics. It's regarded as one of the great foundational results in physics of the 20th century. So if we come back to our model, this model can be physically realized in quantum mechanics. This is the key point. We showed this model before, and it was just an abstract model, and we showed that it was inherently contextual, but it does correspond to a real experience that we can build in which Alice and Bob would really see these things. By using a suitable entangled state of two qubits and suitable directions for the spin measurements, which would then generate this table according to the predictions of quantum mechanics. Now, I'm going to cheat a bit here and not show you the actual state and the spin directions that would achieve this, because they'd be rather ugly numbers. But it is a matter of pure calculation if you come up with the right numbers to show that quantum mechanics yields this kind of behavior, predicts this kind of behavior, and moreover, behavior of this kind, not in exactly this form, but in a related form, has been extensively experimentally confirmed. So this really is how the world is, and we can build systems that have this kind of correlated behavior as a feature. And in fact, what we've just done with our modest piece of reasoning is to prove a strong version of Bell's theorem. So, hey everybody, we proved Bell's theorem. That's good. It's a strong version because we didn't have to use any probabilities. The original kind of proofs used probabilities. Here we only used possibilities, zeros and ones. So we used nothing more than a little bit of elementary logic. Okay, well let's just reflect a little bit on this general situation we're looking at. Having looked at this specific case, let's see what's going on in general. So let's anatomize this table. And the reason I'm going to do this, not in too much detail, is because we're going to find that the structure inherent in this table actually appears in something which every computer scientist knows all too well. It's isomorphic, so it's not so easy to spot when it's laid out in this form, but it's there. And part of the point of developing a structural account of these ideas is we can identify the same structure in different settings. So Bill mentioned the unreasonable effectiveness of category theory. One of the aspects of that is exactly that it lets you identify the same structure in apparently very different settings and make connections between them. So the measurement, what are these rows? These rows are the measurement context, the measurements that can actually be performed together. So if you think, and then we have these events here. So for example, the event where we measured with the variables a prime and b, and a prime was seen to have the value 0 and b was seen to have the value 1. That could just be described by a little function. So we have functions which are just maps from the cells, as it were, that populate the table just correspond to functions from the context, the set of measurements we're performing on that row, into the possible outcomes, in our case 0 or 1. And what the row as a whole is doing is just giving us a set of these things. It's labeling them all with zeros and ones, so it's giving, if you like, a Boolean distribution, which you can just think of as a set. Of course, we could also think of probability distributions, but we're going to avoid probabilities. So there's actually a kind of geometric structure here, and which gives us a very nice way of explaining, of giving a geometric correspondence to these phenomena of contextuality that we've been looking at. We have these local descriptions relative to a context. That's why we're talking about contextuality and contextual semantics. And these local descriptions are these local sections, functions just from a little set of variables that we could actually measure together, say A1 and B2 and so forth in the example we were looking at. And the fact that the behavior of these observable outcomes cannot be accounted for in some context-independent way by a global description of reality, so that's the sort of physical story that we've been telling, corresponds to the geometric fact that these local sections cannot be glued together into what in the jargon is called a global section. So just to get an intuition for this gluing, let's take a familiar example, functions. So we have functions defined on sets, and it's a familiar fact that if the functions agree on their overlap, in other words, they restrict to the same thing on the parts of their domains that overlap, you can glue them together in a consistent way to form a function on the big set. So that's a case where we can glue things together. From a computer science point of view, you might like to think of unification, which is the same, in a sense, what we're talking about with gluing is a semantic form of unification. So in geometric language, the Hardy paradox corresponds to the fact that there's a local section which cannot be extended to a global section which is compatible with all our constraints, compatible with this family of Boolean distributions. So to use the sort of language one might use geometrically, we can say the space of local possibilities is sufficiently logically twisted to obstruct such an extension. And the quantum phenomena of non-locality and contextuality correspond exactly to the existence of obstructions to global sections in this sense. Now, having done this little step of abstraction, the nice point is that this geometric picture and the associated methods can actually be applied to a wide range of situations in classical computer science. And in particular, as we'll now see, there's an isomorphism between the formal description we've given for these quantum notions of non-locality and contextuality and the basic definitions and concepts in, of all things, good old relational database theory. So, to be surprising. So we've all seen these tables, haven't we? So this is a table in a relational database, the sort of column names, the sort of attributes, field names, and then a set of tuples. And the tuples assign values to each of these things. So here's one tuple, branch name is Cambridge, and so forth. This is an early example of scientific cooperation, by the way. Although as you see, they didn't agree on the currency. Okay, so what is a table in a relational database? The columns are determined by a set of attributes. So we have a database schema which says here the database has a set of tables, is a sort of syntactic part, and each of them is defined as a table over the following set of attributes. For each attribute, you have a set of data values, and we'll just munge them all together. And an a tuple is can be written as a function. I mean, there are two ways of writing tuples. This is the one that one very often sees. It's sort of more intuitive in some sense, and actually fits well with our account. So a tuple is just a function from the attributes into the data values. And a relation instance or table is just a set of a tuples. A database schema is a family, I mean, forgetting about dependencies and so on, is just the syntax is just a family of these finite subsets. And a database instance is given by a family of relation instances, relation tables, each of the appropriate schema. So I hope this is starting to look familiar in terms of our, of course this should be much more familiar to any computer scientist, but I hope it's starting to look a bit similar to what we've been discussing. And in fact, databases in exactly this classical form are entirely equivalent to possibility tables. An a tuple is just a local section over the set of attributes A for that table. A relation table is a Boolean distribution on a tuples. And you have this notion of restriction, which is part of this geometric picture I was mentioning, which is just the familiar operation of projection. We take all the tuples and cut them down to the subset of attributes that we're interested in. And then we have this family of sets of attributes defining the schema, and that's the family of sets of measurements we can make together. And a database instance is a family of elements like this. And then saying that instances are compatible is just, rather like in the gluing thing we were looking at earlier, the functions had to agree on their overlap, is just a sort of projection consistency, that the family of relations is mutually consistent in that they have common projections on the overlap of their attributes. So actually, I mean, the thing is that to see the correspondence, each relation table corresponds to a row of the possibility table. It's a distribution on tuples for that set of attributes, that context, if you like. So each table corresponds to a context, and the whole database instance corresponds exactly to the possibility table. So what we've just seen here is that there's a sort of isomorphism between what we may think of as the homely world of databases and the exotic world of physics. So if that's true, and by the way, conceptually, you can just think that the different tables are giving us different slices through the reality of whatever the attributes, I mean, the individuals that we're talking about in the world through the database. And of course, we're just choosing to look at different bundles of attributes in talking about the world. And the question is, how does this hang together? Well, if I've said there's an isomorphism, then it should follow that there's something that corresponds to the notion of contextuality. in short, that if you like, that there's a sort of Bell's theorem hanging around in the world of databases. And actually, the answer is not hard to find. It's the classic notion of universal relations. So and this goes back to the sort of heroic age of, early age of relational database theory. It was actually extensively studied by many leading researchers of the time, Fagin, Vardy, and others. A universal relation is a relation over the whole set of attributes. So this is this global instruction set, if you will, which allows us to retrieve all the relations in the table. Its projection down onto each local set of attributes defining a table in the database gives us back that relation in the instance. So if such a thing exists, then we say that we have a universal relation for the instance. And it was realized early on that this was a very convenient assumption to be able to make, and also that it didn't always hold. And there's a whole literature about this. So a universal relation instance corresponds exactly to the notion of global section in this way. And actually, it's easy enough to check result that a database instance has a universal relation if and only if that collection of relations has a lossless natural join. A natural join, the usual sense of relational database theory, which gives us back the relations we started off with by projection. And if that's true, then it's the largest such universal relation. So what we get is a complete dictionary between relational database world and measurement, and the measurement scenarios, the setting for contextuality that we've been discussing. And this goes a bit deeper than we really have time to discuss. There's actually a deep result about when we can glue probability distributions together based on a combinatorial condition on the sets of measurements, which comes from the Soviet literature on game theory, actually, of all things. And the condition, the necessary and sufficient condition in this rather beautiful theorem is exactly equivalent to the well-studied notion of acyclicity of database schemes. And there's really quite a lot more that can be said. And there's, of course, we can look then at generalizations and some of the things that are actually being studied in current working databases. So why do such similar structures arise in apparently different settings? So one answer is that the phenomenon of contextuality is pervasive. Actually, if you think about language, natural language, meaning in natural language is highly contextual. And even in many computer science settings, the same is true. Once we start looking for contextuality, we can find it everywhere. And so to speak, the contextual semantics hypothesis is that we can find common mathematical structure in all these manifestations and develop a widely applicable theory. Okay, well, just very briefly, let me say that, of course, I've just given a few ideas here, but it can be taken a lot further, both within the world of quantum information and also beyond in classical computation. And actually, this is not a to-do list. There's actually substantive results on almost all of these. For example, there's, I think, a very nice characterization of Bell inequalities in terms of logical consistency conditions. So we didn't look at that in this talk, but I think it's useful because of its generality. And also some insights into what's known to be the elusive structure of multipartite entangled states, to give another example. And then beyond quantum, some recent work with Georg Gottlob and Fokion Kalaitis, because the database discussion is actually very close to the world of constraint satisfaction, which is a major algorithmic paradigm. You're really looking, you can think of the different rows as expressing different constraints, and then the global section is exactly like a solution, a global assignment to all the variables which meets all the constraints. So it's very close to constraint satisfaction. But the Hardy argument that we looked at suggests a refinement to the classical constraint satisfaction paradigm, which has led to what we call robust constraint satisfaction in this recent work, where you're looking at constraint satisfaction problem given that you fix the values of some of the variables. And there are actually several good reasons for being interested in that refinement. For example, because of freezing phenomena that happen because of phase transition effects in satisfiability and so on. At any rate, that sparked a very nice collaboration with Georg Gottlob and Fokion Kalaitis. And another direction is indeed in natural language semantics, which seems a very appropriate field for looking at contextual semantics. And there's some work with Manoush Sadrazadeh, which is really looking at this gluing as a kind of semantic unification and applying it to the well-known tricky issue of anaphora resolution, so famously expressed in terms of donkey sentences. The farmer has a donkey, he beats it. We all know that he is the farmer and it is the donkey, but how did we do that? Surprisingly difficult to say. Anyway, just let me say that if you want to take a bit of a deeper view into these ideas, or a bit more detailed view, which gives an overview and references and so on, there's a forthcoming article in this Logic in Computer Science column of Bulletin of the ATCS. Okay, so of course the work I've been describing has not been that of myself alone. It's been done by any means, and it's been a great pleasure to work with many colleagues who are some of whom are here, at least, and I think we're going to hear from one of them shortly. I mentioned Fokion and Georg. Well, actually, I've got all the names here. Lucian Hardy, same Hardy that was being mentioned earlier. Shane Mansfield, Rui Barbosa, Ray Lal, students and postdocs at Imperial, also Carmen Constantin and Kohei Kushida. And more broadly, it's benefited a lot from interaction with this thriving quantum group in Oxford. That's a picture from last year. And of course, going back now to the picture we showed from 20 years earlier. So there's, so what persists and what endures? So the final thought I'd like to finish up on, going back to, some sense, the starting point, is that I really do believe that even more than ever, that computer science is a fundamental science, but it's also a fundamental discipline among the sciences, participating in and interacting with the sciences in general, as well as, of course, underpinning a central technology in our world. It's important both for its modes of thought and for its subject matter. So the subject matter is, if you like, information, processing, transformation, storage of information, and so on. But also the modes of thinking that we've had to develop in order to deal with the complexities of information processing systems give us all kinds of tools and perspectives in modeling, in thinking, in mastering complexity, and so on, that I think can be very widely applied in the sciences. So it's not isolated from the natural sciences in particular, other kinds of sciences as well, but rather has enormous potential for interaction with them. This vastly transcends merely bringing the computer. It provides fundamental tools for modeling and articulating the structure of the systems we study. So the thing I'd like to say, particularly perhaps for students and young researchers, is we shouldn't limit our scope. We should dare to think big. And on that note, I'd just like to thank you all very much for joining me on this venture tonight.